So, right now, while you are watching this, there is a machine 15 billion miles from Earth, running on less power than the light inside your refrigerator, that is detecting something in the space between stars that should not be there. It was built in the early 1970s, with technology that would be embarrassed by the phone in your pocket. It was designed for a 5-year mission to photograph Jupiter and Saturn, and then to die. That was 48 years ago. It did not die. It kept going, past Jupiter, past Saturn, past Neptune, past the edge of everything the sun can touch, into a region of space that no human-made object had ever entered, carrying instruments that were never designed for what they are now measuring, powered by a fuel source that is slowly, irreversibly decaying, transmitting on 22 watts of power, which is less energy than the bulb above your kitchen stove. Nobody predicted it would survive this long. Nobody designed it for interstellar space. Nobody programmed it to listen for sounds in the void between stars, because no model of the interstellar medium predicted there would be sounds to hear. The scientists studying the data Voyager 1 is sending home are not using words like interesting or unexpected. They are using words like impossible, unprecedented, and confirmed for the first time. Because what Voyager is detecting in interstellar space contradicts the models that were built to describe it. The space between stars is not what anyone said it would be. It is not quiet. It is not empty. It is not the cold, dead, featureless vacuum that generations of astrophysicists assumed it was. It is alive with structure, turbulence, density fluctuations, and a continuous sound that has been humming, without interruption, since at least 2017. And in 2023, this machine nearly died. Its signal turned to gibberish for 5 months. A single memory chip, a component smaller than a postage stamp, failed inside a computer designed before the invention of the personal computer, sitting 15 billion miles from the nearest human being. And NASA engineers, from a control room in Pasadena, California, repaired it, remotely, by rewriting 46-year-old software, one command at a time, with each command taking 22 hours to arrive. They brought it back. And what it has been sending home since is rewriting what we thought we knew about the universe beyond our sun. A continuous sound that never stops. Temperatures that should not exist at the edge of the solar system. Plasma getting denser, not thinner, as it moves deeper into the void. And a clock that is ticking, because Voyager's power supply is dying. Instruments are being shut down one by one, and the window to hear what the interstellar medium is telling us is closing. Stay with me, because by the time this is over, you will never think about the night sky the same way again. You will understand that we have exactly one machine capable of listening to the space between stars, one, in all of human civilization, and it is dying. And what it is hearing, in its final years, is something nobody expected to hear. I am Graham Prescott, and if stories like this are what you come here for, subscribe right now because we are just getting started. September 5th, 1977. Cape Canaveral. A Titan II rocket lifts off carrying a spacecraft that weighs roughly 800 kilograms and carries 11 scientific instruments powered by 3 radioisotope thermoelectric generators, fueled with plutonium-238. The mission is straightforward. Fly to Jupiter, take photographs, measure magnetic fields and radiation. Fly to Saturn, do the same. After Saturn, the mission is over. The spacecraft was given a 5-year operational lifespan. That was the design specification. 5 years, 2 planets, and then silence. Nobody at NASA, nobody at JPL, nobody on the Voyager design team expected the spacecraft to survive much beyond the early 1980s. The radiation at Jupiter alone was expected to severely degrade the instruments. The cold of deep space was expected to freeze the lubricants. The electronics were built with 1970s components that were never rated for decades of continuous operation in the harshest environment the universe offers. Voyager was a short-range sprinter sent on a one-way trip with an expiration date. Designed for 5 years, it has lasted 48. What happened between 1977 and now is one of the most extraordinary stories in the history of exploration, and most people have no idea how extraordinary it actually is. Voyager 1 reached Jupiter in March 1979 and returned images so detailed they transformed our understanding of the gas giant's atmosphere, its ring system, and its moons. It discovered active volcanoes on Io, the most volcanically active body in the solar system, capturing plumes of sulfur rising hundreds of kilometers above the surface of a world that everyone had assumed was geologically dead. It revealed the intricate banded structure of Jupiter's atmosphere in resolution no one had thought possible. It reached Saturn in November 1980 and revealed the astonishing complexity of the planet's ring system, showing that what appeared from Earth as a few broad bands was actually composed of thousands of individual ringlets, braided and sculpted by gravitational interactions with shepherd moons. It made discoveries about Titan, Saturn's largest moon, detecting a thick nitrogen atmosphere that hinted at conditions that might someday, under the right circumstances, support chemistry complex enough to resemble biology. After Saturn, NASA faced a decision. The primary mission was complete. Jupiter and Saturn had been photographed, measured, and analyzed. The spacecraft had done everything it was designed to do. The engineers could have shut it down. Some argued they should, to preserve the budget for other missions. Instead, NASA chose to keep going. Voyager was pointed toward the outer solar system, with no specific destination, no particular target, just outward. Further and further from the Sun, moving at roughly 38,000 miles per hour, 17 kilometers per second, a speed so fast it could cross the entire United States in about 5 minutes. And it kept going. Through the 1980s, through the 1990s, through the 2000s. And the instruments kept working. The radio kept transmitting. The plutonium kept decaying, slower every year, but enough. For decades, Voyager coasted through the outer solar system. Its instruments continued to function far beyond their design life. Its radio continued to transmit, sending data home across distances that grew larger every day. The plutonium continued to produce heat, which the thermoelectric generators converted into electricity. The wattage declined every year as the plutonium decayed. Slowly, predictably, 4 watts less each year, but the spacecraft adapted. NASA engineers turned off non-essential systems one by one, conserving power for the instruments that mattered most. The cameras were powered down in 1990, but not before Voyager took one final image. At the suggestion of Carl Sagan, the cameras were turned back toward the inner solar system one last time, and Voyager photographed the Earth from a distance of nearly 4 billion miles. In that image, the famous pale blue dot, our entire planet is a single pixel, a tiny speck of light, less than 1/10 of a pixel wide, caught in a scattered beam of sunlight. Everything that has ever happened in human history, every war, every love, every birth, every death, every song, every prayer, every moment of every life ever lived, happened on that speck. Sagan wrote about it afterward. Look again at that dot. That's here. That's home. That's us. After that photograph, the cameras were turned off for good. Voyager flew blind from that point forward, but not deaf. Its instruments kept measuring. Its radio kept calling home. And the signal, faint, impossibly faint, a whisper across the void, kept arriving at the Deep Space Network's giant radio dishes in California, Spain, and Australia. 22 watts of transmission power across billions of miles. It takes 22 hours for that signal to reach Earth. One way. A round trip, a command sent and a response received, takes 44 hours. Nearly 2 full days to have a single exchange with a machine older than most of the people reading this. Through the 2000s, Voyager approached the boundary that separates our solar system from interstellar space, the heliopause, the outermost edge of the sun's magnetic influence, where the solar wind pushes outward and the interstellar medium pushes inward, and the two pressures reach an equilibrium that forms a boundary. Models predicted what Voyager would find when it crossed that boundary, a gradual, quiet transition. The solar wind would fade, the cosmic ray intensity would increase, the magnetic field would change direction. It would be subtle, measured, almost anticlimactic, a slow fade from one environment into another, like walking from one room into the next. On August 25, 2012, Voyager 1 crossed the heliopause. It was the first human-made object to enter interstellar space. The moment was confirmed by a sudden change in the plasma environment around the spacecraft, a drop in solar wind particle density, and a dramatic increase in galactic cosmic ray intensity, exactly the signatures the models predicted for the crossing itself. But the conditions it encountered at the boundary were nothing like the models said they would be. Temperatures at the boundary approached 30,000 degrees Celsius, not in the sun, not near a star, at the outer edge of our solar system, in a region that every model predicted would be cold and quiet. 30,000 degrees. To put that number in context, the surface of the sun is approximately 5,500 degrees Celsius. The heliopause boundary that Voyager crossed was hotter than the surface of the sun itself. The boundary was not a gentle fade, it was a wall of fire. Magnetic reconnection events, where magnetic field lines from the sun and from the interstellar medium collide and violently reconfigure, releasing enormous amounts of energy. Plasma interactions so turbulent that the data looked chaotic. A dynamic, shifting, violent interface that bore no resemblance to the clean mathematical line that the textbooks described. Models had predicted a gradual, smooth transition. Voyager found a furnace, and it walked through it, and it survived, and its instruments recorded every second of it and sent the data home at the speed of light across 15 billion miles. And the models had to be rewritten, because the edge of the solar system was not what anyone said it would be. Designed for 5 years, it has lasted 48, and what it found at the edge of the solar system was the first proof that everything we thought we knew about that boundary was wrong. But the wall of fire was not the impossible discovery. It was surprising. It was significant. It rewrote the models of the heliopause. But what Voyager found after it passed through the wall, in the space beyond, in the void between stars where every model predicted silence, that is the part that should not be possible. Let me explain what Voyager heard, because the simplicity of it is what makes it extraordinary. Voyager 1 carries an instrument called the plasma wave system. It detects vibrations in charged particles, measuring the frequency and intensity of oscillations in the plasma that fills the space around the spacecraft. After crossing the heliopause, the plasma wave system detected occasional sharp whistles, plasma oscillation events triggered by shock waves propagating outward from the sun. These were expected. Solar eruptions send shock waves through the heliosphere and beyond, and when those shock waves reach Voyager's location, the plasma rings like a bell. These events occurred roughly once a year. They were useful for measuring the density of interstellar plasma at specific moments. But between those events, the expectation was silence. The interstellar medium, far from any star, far from any energetic source, should be still, quiet, dead. In 2021, Stella Koch-Acker, a doctoral student in astronomy at Cornell University, found something hiding in the Voyager data that nobody expected. A faint, continuous, narrowband emission that had been persisting in the plasma wave system data since at least 2017. Not triggered by solar events. Not intermittent. Not correlated with anything from our sun. A persistent, monotone hum. Continuous, year after year, never stopping. It's very faint and monotone, because it is in a narrow frequency bandwidth, Acker said, when the discovery was published in Nature Astronomy. The signal was hiding just above the noise threshold of the plasma wave system instrument. She described what Voyager was detecting as the faint, persistent hum of interstellar gas. Her senior colleague James Cordes at Cornell put it differently. The interstellar medium is like a quiet or gentle rain, he said. Between the occasional thunderclaps of solar shock waves, there was this steady drizzle that nobody had ever heard before, because nobody had ever had an instrument out there to hear it. Think of it this way. You are standing in what you were told is a perfectly silent room. You have been told that nothing is happening in this room, that it is the quietest place in the universe, that between the rare thunderstorms that pass through it, there is nothing. Absolute stillness. You hold your breath, you listen, and you hear it, a low, steady hum, right at the edge of what your ears can detect, and it never stops. It has been going on, without pause, since at least 2017, maybe longer, maybe always. That is what Voyager is hearing in interstellar space. A sound in a place where sound was not supposed to exist. What the hum reveals is that the interstellar medium has structure. It has texture. It has turbulence operating at scales of astronomical units, the distance between Earth and the Sun used as a measuring stick. The density of the plasma fluctuates as Voyager moves through it, and those fluctuations trace turbulence, the chaotic churning of gas in the vast spaces between stars. The space between stars is not still, it is active, and the hum allows scientists to track that activity continuously, without waiting for solar shock waves. We don't need a fortuitous event related to the sun to measure interstellar plasma, said Shami Chatterjee, also at Cornell. Voyager is saying, here is the density I am swimming through right now, and here it is now, and here it is now, and here it is now. Now stop and sit with that for a second. A machine running on 22 watts of power, designed in the 1970s to photograph Jupiter, is detecting a continuous sound in the space between stars that no model predicted and no other instrument in human history has ever heard. And the plasma density is not behaving the way the models said it would. As Voyager moves deeper into interstellar space, the density has been increasing in certain regions. A large-scale density gradient has been detected outside the heliopause. Denser, not thinner. More material, not less. The space Voyager is moving through is getting heavier. But here is the part of this that stops being abstract science and starts being personal. Because the interstellar medium is not just empty space that Voyager happens to be passing through. It is the environment that presses against the heliosphere, the magnetic bubble that shields our entire solar system from galactic cosmic radiation. The heliosphere exists because the solar wind pushes outward, and the interstellar medium pushes inward. And where those pressures balance, a boundary forms. Everything inside that boundary is shielded. Everything outside it is exposed. A turbulent, active, structured interstellar medium means the heliosphere is under variable pressure. More pressure on the outside means the boundary gets pushed inward. The shield shrinks. And if the interstellar medium is denser and more turbulent than the models predicted, which is exactly what Voyager's hum is revealing, then the shield that protects Earth and every living thing on it from the full radiation environment of the galaxy is under more stress than we calculated. We know from geological evidence that approximately 2 million years ago, the heliosphere was compressed so severely that Earth was exposed directly to interstellar space. The hum is telling us the environment that caused that compression is more complex and more active than anyone realized. Either the models of the interstellar medium are wrong, or the heliosphere is less stable than we assumed. Both options require rewriting what we know. And the only instrument telling us this, the only machine capable of making these measurements directly, in situ, with no intermediary, is a spacecraft that was designed to last 5 years and is running on borrowed time and shrinking power. And here is where the story gets stranger. Because in November 2023, Voyager 1 nearly died. And the way it nearly died, and the way it was saved, is one of the most extraordinary engineering stories in human history. On November 14, 2023, Voyager 1 stopped making sense. The spacecraft, 15 billion miles from home, traveling at 38,000 miles per hour through interstellar space, older than most of the engineers responsible for keeping it alive, began transmitting a steady stream of data that meant absolutely nothing. NASA described it as a repeating pattern of ones and zeros carrying no information. The radio link was fine. The probe was receiving commands from Earth and, by all indications, executing them. It was alive. It was listening. It just could not form a coherent sentence anymore. For 5 months, this continued. November, December, January, February, March. 5 months of gibberish from the most distant machine humanity has ever built. Suzanne Dodd, the Voyager project manager at JPL, later called it the most serious issue we've had since I've been the project manager. And her voice, when she said it, carried the weight of someone who understood that losing Voyager was not losing a spacecraft. It was losing humanity's only ear in interstellar space. The diagnosis took months of the most painstaking, slowest troubleshooting process in the history of engineering. Each diagnostic command sent from Earth took 22 hours to arrive at the spacecraft. Each response took 22 hours to come back. A single question and answer cycle took nearly 2 full days. And because the spacecraft was sending gibberish, the team could not simply ask it what was wrong and receive a clear answer. They had to send probing commands, tiny nudges designed to trigger specific responses from different subsystems, and then read the gibberish that came back, looking for patterns in the noise that might indicate which part of the system was corrupted. It was like trying to diagnose a stroke patient who can only respond with random syllables from a distance of 15 billion miles, with a 2-day lag between every question and every answer. Slowly, painstakingly, over weeks and then months, the team narrowed the problem to the flight data subsystem, the onboard computer responsible for gathering data from the instruments and packaging it for transmission. Within the FDS, they identified the culprit. A single memory chip had failed. One chip. It held approximately 3% of the FDS memory, and that 3% included part of the software's own operating code. The computer was trying to run programs stored in a region of memory that no longer worked. It was pulling instructions from a damaged area, like a brain trying to speak from a region that has been damaged. The words come out, but they carry no meaning. The data formats, but it formats wrong. Everything the instruments measure gets scrambled before it ever reaches the antenna. The fix was the kind of thing that sounds simple when you describe it and is almost impossible when you try to do it from 15 billion miles away. The engineers broke the affected code into pieces small enough to fit into spare corners of the FDS memory that were still functional. Then they relocated each piece, one at a time, sending commands that took 22 hours to arrive, waiting another 22 hours for confirmation that the command was received and executed correctly. Think about what that engineering process actually looked like from inside the control room. You type a command, you check it again, you send it. And then you sit in a chair for 22 hours, watching the clock, not sleeping, not knowing whether you got it right, knowing that if one bit is in the wrong place, if one address is wrong, if one pointer is broken, you might lose the most distant machine humanity has ever built. And then you wait another 22 hours for the reply. One command. 44 hours. That is the rhythm of saving something 15 billion miles away. On April 18, 2024, the first corrected code was transmitted. 22 hours of silence followed. Then, on April 20th, the response arrived. Valid data, coherent, readable. Voyager was speaking again. By June 2024, all 4 science instruments were back online, returning measurements from interstellar space for the first time in 7 months. In November 2024, another scare. Voyager inadvertently switched to its low-power backup transmitter, weakening its signal. The team fixed that too. Designed for 5 years, it has lasted 48. And in 2024, a team of engineers who were not born when Voyager launched used code written before most of them existed to save it from a single failed chip smaller than a postage stamp in a computer sitting 15 billion miles from the nearest human hand. They saved it. And what it has been sending home since is exactly what nobody expected. The hum was still there, continuous, unchanged, persistent, as though nothing had happened, as though 5 months of gibberish and a dead memory chip and the most difficult remote repair in the history of engineering had not occurred. The interstellar medium had continued humming the entire time Voyager was unable to hear it, and the moment its ears came back online, there it was. The same frequency, the same narrow band, the same gentle rain that had been falling since 2017. The density measurements continued, revealing turbulence and structure in the interstellar medium that no model had predicted. New density fluctuations were detected at AU scale, adding data points to a map of the interstellar environment that only one instrument in all of human civilization can draw. Voyager came back from the dead and immediately went back to rewriting what we know about the universe between the stars, as though it had no intention of stopping, as though dying was not on its schedule. Not yet. But Voyager's resurrection came with a cost, because the power supply that keeps it alive is not recovering. It is dying, and it cannot be stopped. Voyager 1's power comes from 3 radioisotope thermoelectric generators that convert heat from the decay of plutonium-238 into electricity. In 1977, those generators produced approximately 470 watts. In 2026, they produce approximately 220 watts. That is less than 47% of their original output. And they lose roughly 4 watts every year as the plutonium decays. This is not a malfunction, it is physics. Radioactive decay follows a half-life. The plutonium is cooling, the power is declining, and nothing can be done about it. Each of Voyager's science instruments uses about 4 watts. The radio antenna, the system that sends data home across 15 billion miles, uses approximately 200 watts. That means the entire spacecraft, all its instruments, all its computers, its heaters, its radio, everything, runs on less power than 2 household light bulbs. And every year, 4 more watts disappear. In February 2025, NASA turned off the cosmic ray subsystem. This was the suite of 3 telescopes that helped determine the exact moment and location where Voyager crossed the heliopause in 2012. It was one of the instruments that confirmed humanity's entry into interstellar space. It is now gone. 3 instruments remain: the magnetometer, the plasma wave system, and the low-energy charged particle detector. The LACP is scheduled to go dark in 2026. After that, only 2 instruments will remain: the magnetometer, which measures the interstellar magnetic field, and the plasma wave system, which hears the hum. These are the instruments that matter most for understanding the region Voyager is passing through. They have been kept alive for exactly this reason. They will be the last to go. The spacecraft is expected to continue returning science data through the late 2020s. After the last instrument is turned off, Voyager may still transmit a faint carrier signal, a simple tone confirming it is alive, like a heartbeat with no voice behind it, possibly into the early 2030s. After that, silence, permanent, irreversible. The radio will go quiet. The antenna will still point toward Earth, but there will be nothing coming out of it. The Deep Space Network dishes in California and Spain and Australia will listen on the frequency they have been listening on for nearly 50 years, and they will hear nothing. And there is nothing on any drawing board, in any budget, at any space agency on Earth, that can replace it. No interstellar probe is funded. No interstellar probe is designed. No interstellar probe is planned. The Interstellar Probe Concept Study, which proposed a dedicated mission to the interstellar medium, has not been funded for development. Even if it were funded tomorrow, design and construction would take over a decade, and the journey to the heliopause would take at least another decade. We are looking at a minimum of 20 to 30 years before any new machine could reach the region where Voyager is now. In that time, the interstellar medium goes unmeasured, the hum goes unheard, the density fluctuations go untracked. Everything Voyager is telling us about the environment between the stars simply stops being told, indefinitely. Designed for 5 years, it has lasted 48, and every year it survives now is a year of data that no future generation will ever be able to replicate, because there will not be another Voyager, not in our lifetime, probably not in our century. But even when the last instrument goes dark, even when the power finally runs out and the signal stops and the most distant machine humanity has ever built goes silent for the last time, Voyager 1 does not stop. It keeps moving, 38,000 miles per hour, 17 kilometers per second, outward, into the interstellar medium, through the darkness between stars, carrying something that does not need power and does not need watts and does not decay. Bolted to the side of the spacecraft is a golden phonograph record. It is 12 inches in diameter, made of gold-plated copper, with a protective aluminum cover electroplated with uranium-238 that will serve as a radioactive clock, allowing any civilization that finds it, in any era, to calculate how long ago it was made by measuring how much of the uranium has decayed. The cover is engraved with instructions for playing the record, written in a symbolic language designed to be understood by beings who have never seen a human being, never heard a human language, and may not share any of our assumptions about the universe except the laws of physics themselves. The record contains greetings in 55 human languages, from Akkadian to Wu Chinese. 90 minutes of music, chosen by a committee chaired by Carl Sagan, ranging from Bach's Brandenburg Concerto No. 2, to Beethoven's Fifth Symphony, to Chuck Berry's Johnny B. Good, to Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless slide guitar piece recorded in 1927 by a blind street musician in Beaumont, Texas, that Sagan considered one of the most emotionally powerful recordings ever made. The sounds of earth, wind across a plain, rain on a surface, thunder in the distance, birdsong at dawn, whale song in the deep ocean, the sound of a heartbeat, a baby crying, a mother's first words to her newborn child, images encoded in analog format, a diagram of our solar system, a photograph of a woman nursing an infant, a picture of a supermarket, a highway, a human being eating, a sunset, the mathematical structure of DNA, and, in what may be the most extraordinary artifact any civilization has ever launched into space, the recorded brainwaves of Anne Druin. She sat in a laboratory at Bellevue Hospital in New York, electrodes attached to her scalp, and for 1 hour she thought. She thought about the history of Earth. She thought about human beings. She thought about war and peace, and art, and music, and what it means to be alive on a small planet orbiting an ordinary star. And she thought about falling in love, because 2 days earlier she and Carl Sagan had confessed their feelings for each other. Those brainwaves, the electrical patterns of a human mind contemplating the full sweep of human existence, while simultaneously experiencing the most intense personal emotion a human being can feel, were compressed into analog signal and pressed into the grooves of a golden disk that will outlast every building, every monument, every written record on the planet it came from. The golden record will survive in interstellar space for at least 1 billion years. In approximately 40,000 years, Voyager will pass within 1.6 light-years of a star called Gliese 445. After that, it will continue. It will orbit the center of the Milky Way galaxy, silently, for billions of years, long after the sun has expanded and consumed the Earth, long after every civilization that exists today has risen and fallen and been forgotten. The record will still be there, carrying the sound of rain, and a baby's cry, and the brainwaves of a woman thinking about love. One machine, 22 watts, 15 billion miles, designed for 5 years. It has lasted 48. And in the time it has left, however many months or years of power remain in those cooling pellets of plutonium-238, every signal it sends, every measurement it takes, every faint vibration of the interstellar hum it detects, is something no human ear will ever hear again once it goes silent. We have exactly one machine in interstellar space, one, built with technology from the 1970s, running on a power source that loses 4 watts every year and cannot be recharged, refueled, or replaced, carrying instruments that are being turned off one by one as the power budget shrinks. And it is hearing something out there, in the space between the stars, in the vast cold emptiness that separates our sun from the next nearest sun, that we did not know existed. A continuous hum, a gentle rain in the void, a sound that will stop reaching us not because it stops existing, but because the only thing we ever built that can hear it will finally run out of power to listen. The question is not whether Voyager 1 matters, The question is whether anyone is paying attention, because the hum is still coming, and Voyager is still listening, and it will not be listening for much longer. If this kind of story is what you come here for, subscribe right now and turn on notifications, because next time we are covering what happens when Voyager's last instrument goes dark, and why no space agency on Earth has a plan to replace it. Drop a comment with what hit you hardest. The hum nobody expected, the brain surgery from 15 billion miles away, or the fact that when Voyager goes silent, we lose our only ear in interstellar space. And share this with someone who needs to hear it, because this story deserves more than the silence it is getting. And silence is exactly what is coming, sooner than anyone wants to admit.